Swayam Prabha. Digital India. Educated India.
Today, I'm going to discuss an interesting aspect of thermodynamics, and that is related to entropy and its interpretation in a different way. So let us begin by noting that whenever we talk about thermodynamics, it means you have a very large system, very large volume, and the number of particles which are residing inside inside the box or the volume is very large. So the volume is very large, and number of particles inside, they are also very large. In fact, both tends to infinity, but the density remains finite. That is called a thermodynamic system. So by thermodynamic system, so by a thermodynamic system, we mean a very large volume occupied by the system V, and large number of particles, say N. So that, and both goes to infinity. So but the density, that is N by V, that remains finite. That means N is large, V is large, and large to the extent that it is very, very large. And if both are large, but the division is such that it remains finite. So that is, in general, we call a thermodynamic system or macroscopic system. Now, if we look at it in a macroscopic way, then we know that a system can be specified by certain parameters like temperature, pressure, volume, and we have seen that the two parameters are sufficient to describe it. So to define a macro state, of a system, we consider the first thing, a macro state of a system, thermodynamic system, that is characterized by two parameters like temperature and volume, that is sufficient, and it contains a large number of particles. Let us be more specific about the system, and let us take, it is an ideal gas. So consider an ideal gas. An ideal gas, and it contains say N, the number of particles occupying volume B at a temperature T. So this is a typical consideration that we have given to an ideal gas, and there are n number of particles. So n number of particles are there which are inside a volume V at a temperature T. So the temperature and pressure. So to define a macro state, so macro state is defined by TV. So a macro state can be defined by a temperature and volume. Now look at what these particles are doing inside this particular volume V. That is another question. So you know that since we have considered, if we take the particles as the gas particles, and the particles are moving randomly, and it happens so that that if you can take some picture very fast, snapshots of at different point of time, then what we will see? You will see that the particles are occupying different sites at different time. So for each snapshot will give you a picture, and that is a distribution that is how the particles are distributed inside the box. So that is the interesting thing, and they may be arranged in so many different ways, and depending on time. So as time proceeds, you will see the arrangements changes, and the thing is this, that how to connect these arrangements, if there anything that can be considered that it is related to this micro state, that is the question. So I will try to consider that the next question is the question of this thing that is that I call the micro state of a system. Micro state of a system. So what the N particles are doing that inside it. So take snapshots. Take snapshots inside the box, inside the volume V, and see how the particles are distributed. So that is the thing that we can see now. And how to think about this distribution of particles? So that is the question. So for that, what we will going to do, let us consider that the volume V of the that we have a volume V of this type. Say this is a three-dimensional volume V, and so V equal to the volume, and say d cube. D is the diameter of the particle, so d cube is the volume of the container, and this is d cube is the volume of a particle. D is the diameter of the particle. So d cube, basically the d cube is effectively is the volume. So V by d cube. So V by d cube is a small volume. So I can think of this V can be divided into several small boxes like this. So this is a volume occupied by, say, one molecule. So this is a small box. These are the small boxes which can be occupied by the molecules. So V by D is basically the number of such boxes and number of sites in which I can put the so this is the number of sites. This is the number of sites in which I can put these particles here. Okay, and so and say this number is basically N. Is a capital number, a capital N. So that is the number of sites. 1, 2, 3. Say up that how much what is the order of magnitude of number? We just take it right now. Say for illustration, say V is of the order of 1 meter cube, and D, since D is the diameter, is the order of 10 to the power minus 10 meter for a molecule. So D cube is of the order of 10 to the power minus 30 meter cube. So V by D, V by D cube will be equal to 10 to the power 30. It is a huge number that you can see. It is the number of sites N. So these numbers, if you count it, this is a huge number, 10 to the power 30. Now the N, the number of particles that are considered here. So for N number of particles, we have N particles, and N is of the order of 10 to the power 23. So N is the number of particles is of the order of 10 to the power 23, and the number of sites is of the order of 10 to the power 30. So 10 to the power 30 is much larger compared to 10 to the power 23. So that means we have a situation that N is much greater than small n. This is the first point. And second point is this. So if you draw these molecules are here, and in particles, and this is in sites. So you have N sites here and N particles. So when I'm taking snapshots or the camera photos at still photos at different time, I will see that the particles will be residing at various places. So you have N particles are distributed in various ways that you can imagine. So the question next is the distribution, how the particles are distributed. So that is the important thing, and that will define my microstate. Just as this T and V defines a thermodynamic macrostate, this can be defined by the macrostate. Then we will come to an interesting question that how the particles are, how N particles can be distributed in N sites. So you have N particles to be distributed in N sites. So these particles are to be put in. So for each site you can put one particle, and because this is the volume of each site is governed by the volume of the particle. So you can put it like that. Now you have n particles, so you know the permutation and combination from your class 12 courses. So that is that I will use now. So to start with, let us see that for we have n particles. So for first particle, for particle 1, there are n sites. If I take one of the particles, it can occupy any of the n sites. Any of the n sites. So for particle 1 has n ways, n number of ways for particle 1. For particle 2, what will happen? For particle for the particle 2, for 2 particles, it means one of the sites is already occupied. So one of the sites, one of the n sites is occupied, so that it can be put in n minus 1 ways, one sites. So for 2 particles, it means what? For 2 particles, how many ways I can distribute? For 2 particles, this is the particles for second particle. This is the first particle first. This is second. For 2 particles, so I have n into n minus ways of occupying the sites. So if you have 2 particles, for 3 particles, you have n into n minus 1 into n minus 2 ways of occupying the sites. That means you can distribute 3 particles into n minus 1 into n minus 2 ways. So if you continue in this way, that means for n particles, all that you have, n into n minus 1, n minus 2 to n minus n plus 1 ways can be distributed. So it means what? For n particles, I have this number of ways. There is a product of n into n minus 1, n minus 2 up to n minus n plus 1 ways it can be distributed. Okay, so I have n sites, capital N number of sites and small n number of particles. So they can be distributed in this way. So I call this as W. So I call this as W is the number of ways, W is the number of ways I can put n particles in n sites. So that is basically n into n minus 1 into n minus 2 to n minus n plus 1. So W is what? That is the W is a number, that is the number of ways in which n particles can be distributed in n sites. So this is my W. So W you can think basically is a probability. So we will talk about the probability. Now there is a good way of writing it. So I rewrite this as n into n minus 1 into n minus 2 up to n minus n plus 1 into, then I multiply then this number n minus m to n minus m minus 1, then up to 3, 2, 1. And since I introduced it, I divide it by the same thing. So n minus m minus 1 up to 3, 2, 1. Now see that in the numerator you have n into n minus 1, n minus 2, then go up to 1. So what is this thing? It is factorial n, nothing but factorial n. So this is called factorial n, so that you know. And here n minus m up to 1, that basically n minus n, sorry, it is n. N, so it is n. So it is n minus n factorial n. So W is a number that gives you the number of ways in which these n particles can be distributed in n sites, and that site has been constructed out of the volume V, which is very large, of the order of 1 meter cube, and each site is occupied by a molecule or an atom of the size which is characterized by a diameter d. So that is the thing. So up to this we see that there is an interesting way of writing this W, and this W is called, this is basically the probability. So this is called a thermodynamic probability. Now what we do, and this corresponds to a typical micro each arrangement. So you see that each is an arrangement. That is, I say that n particles are distributed in n sites. In how many ways? That this number of ways. It is a number. This number of ways. So each arrangement is a microstate. So each such arrangement, it gives a number of ways. So each way or each arrangement, so each is called a microstate. So I need a connection between a macro state and the micro state. That is my entire objective. So how to get a connection between a macro state and a micro state? To do this, we consider the two volumes and under or the change in volume under isothermal condition. So I see that W is something that corresponds to the number of microstates, or we may call it the W is the number of microstates. So W is basically n factorial by n minus n factorial is the number of microstates of the system characterized by a macrostate by temperature volume. So corresponding to a temperature T and volume V, this is the number of microstates that we so microstate is nothing but an arrangement of the particles inside this box at different sites. So that is the thing. Each arrangement is a microstate. So the total number of microstates is this number, and this corresponds to a macrostate, entire macrostate V, and so the connection is this. Now I consider a very simple case. I consider isothermal expansion of an ideal gas. So since I considered an ideal gas, so I consider an isothermal expansion of the ideal gas. Consider now isothermal expansion of the ideal gas. Means what? That I have a macrostate at temperature T, volume V1. I go over to another macrostate at a temperature T with volume V2. This is basically the isothermal expansion of the ideal gas. So if this is so, then I expect that the number of arrangements for this between these two will change. So as we go from V1 to V2, because T is not changing, so as I am going from V1 to V2, that is isothermal expansion, in that case this number will also change. Since V, why? Since V is basically, since V is basically V by V is proportional to N. Since V is proportional to N, there is a number of sites. If you increase the volume, the number of sites will be increasing. Since this happens, then the number of microstates will change correspondingly. That means for this state I have a W1 and it will go to W2. Okay, so what is my W1? So W1 I can calculate. What is W? It depends on the number of sites divided by n minus n, the number of particles. So number of particles remains same. So for W1, so W1 is what? W1 is basically n1 factorial divided by n1 minus n factorial, that is W1, and W2 is basically n2 divided by n2 minus n. Since V is proportional to n because of this relation, so V by d cube is basically n. V by d cube is basically n. So d cube is constant. So V is proportional to n. So that means, so if you change the volume V1 to V2, W1 will change, the number of microstates will change from some value W1 to another value W2, and the ratio, and that is given by this ratio n1 divided by n1 minus 1. Sorry, there are factorials. So this, so next thing that what we are going to do is to calculate the ratio of the number of microstates, as a ratio of the number of microstates. But for this, we need the connection, and the entire description is just to connect the microstate with the macrostate in a probabilistic way, and the main idea is to connect entropy with the probability. So main idea behind this is entropy and probability. So in my next lecture, I will proceed with the ratio of the ratio of this for the calculation of W1 and W2, and see what we get for the connections. So thank you.